we were working on calculating area and definite integrals. And remember remember that when we talked about derivatives, we saw there was a long way and a short way to find derivatives. There was a long way and a short way to find the slope of the tangent line. The long way was to approximate the tangent line and then take the limit as the approximations got better and better. Well, now we're learning the long way to calculate areas. The long way to calculate areas is to approximate the area with little rectangles and then take the limit as the number of rectangles increases. Now we're kind of doing this out of order because your instructor's already covered the short way. The short way to find areas is to use antiderivatives, right? The short way to find areas is to use antiderivatives using the fundamental theorem of calculus. But now we're going back and looking at the long way. And we were practicing that.
Okay, cool. All right, so this is our interval, -2 to 3. You need to divide into 5 subintervals, equal length. So that's going to come out to 5 over 5. So each subinterval is going to be 1 unit.
Good.
Okay. Approximate the area under the curve on -2 to 3 using left endpoints. Okay, so we're starting here. All right. So you go up and over, up and over, up and over. This is 1, 2, 3, 4. Alright, I'll do it like this. A, B. Okay, so you can approximate the area. So area equals delta x times one times, this is 1. Alright, so 1 times 1 is 1. 1 times, oh no, that's not right. Okay, -2. 1 times -2 is -2. Plus 1 times -1 plus 1 times
Okay, let me give you some help with that. So you have to start by finding the area of rectangle A, right?
Right.
How wide is rectangle A?
1 unit.
Good. Use your cursor to show me its width.
Okay. Right here?
Good. Why don't we label the x values on the x-axis then so we can see that more clearly. So you can see that from -2 to -1 is 1 unit, and you also figure that out off to the side. Now use your cursor to indicate the height of the rectangle.
Right here.
Okay. How can we figure out how tall that rectangle is?
We can plug x into the function.
That's right. That would be one approach. That's right. Now, in this case, they didn't tell you what the formula for the function was, right? They told you the name of the function is f, but they didn't actually tell you what the formula was that they were using for the function. So we can't quite do it the way you suggested. Let's go back to the. Is there any way you could print out the picture on the website?
Yeah.
Yeah, that would be helpful. So we don't. So on the drawing program again, point out the height that we need to figure out.
Right here.
Yeah. Well, your printout should tell you that height.
Right. Okay. Yeah. I didn't draw this very well. Okay. So my height at x equals -2 for the function will be 2.
Okay. So what went wrong when you were doing this the first time? You were actually plugging in the x coordinates for the heights, right? You were plugging in the x coordinates, but the height is given by the y coordinates, right? Not by the x coordinates. That's why that first approach was incorrect. So we should erase what you have down there for the area, and we can try that again. So how would you calculate the first area?
Okay. So the first area is going to be 1 times 2.
Good. And why don't you relabel your y-axis to put the 2 hash mark up where it should be. It won't be drawn to scale, but at least in your notes you can see where you got that number 2 from. So that 2 hash mark will go up there. Okay, that'll be the number 2. Good. Okay, so then how can we find the area when you're ready for rectangle B? That was a good idea to label those rectangles A, B, C, D, and E. Perhaps you should put those letters above your calculations. So you've done A so far. That was a good idea.
So for B, when x equals -1, the height of the function is...
and you can look at your printout for that.
Somewhere slightly below 3, like 2.75.
Sounds good to me.
Okay.
So they just basically expect you to eyeball it with a reasonable number.
Okay, cool.
All right, and this is certainly something you might see on the test. So the thing that threw you off is this is a little different from the problem you and I did yesterday. Yesterday, I gave you a function with a formula, so we could figure out that heights from the formula. But here, they expect you to figure out the heights from the graph. Well, you might see either of those on the test, so it's important to practice both ways. That number 3 looks like it's pretty much exact. Good.
This one's pretty much the same. And then at 2, oh wait, no, at 3, we're back at 2. Okay, cool. So 2, well, let's add that.
Let's see.
2 plus.
So let's look at rectangle E again. Point to the height that we need from rectangle E.
Right here.
Looks like you're doing the width. Point to the height that we need for rectangle E. What's the height of rectangle E? Use your cursor to show the height from where to where?
From here to here.
Good. And that's at what x coordinate?
2.
So take another look at your printout.
Okay.
I don't think we quite got the right height there.
That's right. So I think I need to remember left endpoints stay left. Okay. So this looks about the same as -1. So something like this.
That's right. So they drew this as a symmetrical graph. So whatever those two numbers are, they should be about the same. Maybe something we should start doing is go to x equals -2 and put a dot on the curve. That's the coordinate that we need for that height. And then put a dot for the next height. No, that's actually not the right height. Yeah, the next height, and then let's put a dot. It doesn't work so well in your picture because your picture doesn't match the printout so well. But if we put in those dots. So is there another dot?
Nope.
No. You have to know when to stop. So how many dots have you drawn?
5.
So notice we never put a dot where x equals 3 because that's not a left endpoint. You were just mentioning a second ago that we were having little trouble with the endpoint. So maybe it would be a good idea to put in those dots to help us keep focused for those ideas. So you can see on these problems, even if you understand it conceptually, it's easy to make careless mistakes. So that's the purpose of the practice, to learn how to get through that without them.
Okay, I get 13.5.
All right, one moment. Okay, so what was the answer to the question?
The area divide, okay. Approximate the area under the curve between -2 and 3, and I got area equals 13.5.
Okay, that's right. How could we make this a better approximation?
We can make this better by, instead of using the left endpoint, we can use the midpoint.
Let's see. It's not really clear to me whether that would make it better or not. Sometimes the midpoint approach is better, sometimes not. What I was going for is the thing that always gives you a better approximation is drawing more rectangles. Right? If we did 20 rectangles, they would match up much more closely, right? In fact, it's kind of foolish to do only 5 rectangles. That's not a great approximation. We're only doing such a low number because otherwise it would be too tedious to do it by hand. So how could we get a better approximation? By doing 20 rectangles. And how could we get the exact area? We could get the exact area by taking the limit as the number of rectangles went to infinity. That's the point of these exercises. Okay, all right. So in any case, this would be a good one to go back and try again because we can see how it's easy to make careless mistakes. So now we should go on to part 2.
Okay, so I can use this graph again.
Now you have to be careful because the graph you drew doesn't totally match the printout. So you have to go back and forth between the printout.
Mm-hmm.
The printout will give you the more exact numbers. Okay, but you can at least draw the rectangles here.
Now we start at 3. We go up to the function.
So since we're trying to draw the rectangles, I think all the sides of the rectangle should be solid lines.
Okay. And then from okay. Okay. And then so we went up and over, up. So up.
That one's tough to draw because the graph doesn't quite match the printout, but that's the right rectangle. Good.
Okay, and then now we go already up, so we just go over. And okay, so this is, well, A, B, C, D. I drew too many. Okay. Alright, so the area is 1 times C. 2 plus 1 times 0.75. So this was A, this was B, this was C. And then for D, we use 0. It's also about 3. And E is that -1, so about 2.
So let's see. So notice you said that C and D have about the same height?
Mm-hmm.
Great. Good. That's correct. Notice that doesn't quite match your picture. In your picture, it looks like D and E have the same height. But on the printout, you can see it's really C and D that have the same height. So I think you did that correctly. Okay.
Okay, so our height should be 2, 2.75, 3, 3, and 2.75. That's what we got. Add them up. 2 plus 2.75 plus 3 plus 3 plus 2.75, and I get 13.5. Got the same as the left endpoint. I guess that's because it's symmetrical.
Yeah, that's true. If you zoom out so we can see both pictures at the same time. So in the top picture, let's see. Okay, yeah, just because of the symmetry, they turned out to give us the same answer in both cases if you actually use the picture on the printout. Okay, that's right. So it doesn't necessarily mean we made a mistake when two answers come out the same. In this case, that's correct. Okay. Oh, did you go back and put in the dots? Yeah.
Mm-hmm.
So that might be a good thing on the test. So this would be good to practice because it's just easy to make careless mistakes. It would be a shame not to get full credit on these. So those are the 2 points. Remember that so in the first problem, the sample points were the left endpoints, and in the second problem, the sample points were the right endpoints. Okay. Well, let's also do the next problem.
Okay. All right, so for A, we're using right midpoint, and we're doing 4 minus 0 on 4 intervals. So 1 unit for each. And we're doing right endpoint. So we're going up. Going up. Right. Okay. So our area equals 1 times that 3. So this is A. B.
Okay, let's go back and think about those areas again. So you were getting the areas off the graph here, right?
Mm-hmm.
So some of the heights you were only approximating, but for this problem we can get the exact heights.
Okay. Okay, so we plug 4 into the function and we get 2. We plug 3 in. Let's do this.
That's a good way to start.
And then plug in 2. And plug in 1. Okay, so now I can add up 2 plus the square root of 3 plus the square root of 2 plus 1. And I get 6.146. Maybe for area, should I just leave it as a decimal?
That's fine with me. I mean, you've already kind of given the exact answer right above.
Mm-hmm.
So that would be fine with me if you left it like that. I mean, if you wanted it to be exactly correct, what's the area of A?
2.
And what's the area? Well, okay, no, actually, so I'm looking at the answer key, and this is how the instructor did it on the answer key. What you just had. So if it's good enough for them on the answer key, it's good enough for us. So
Cool.
oh no, I mean putting in as the decimal they did too.
Okay.
So they wrote it out, and then they also approximated it as decimal. So since that's what they do in the key, we'll assume that will be good enough.
Okay.
Okay, so something that's given us a little trouble on these is how do you figure out the height of the rectangles? We've actually seen two different approaches. What are the two different approaches that we've seen on these problems for figuring out the height of the rectangles?
Sometimes we have to estimate the height if we're not giving the function, and if we are given the function, we have to plug the x values into the function to determine our height.
That's right. So you just have to keep your eyes open. There's two different types of problems. How can you estimate the heights?
By using the graph.
Yeah, just by using the graph. That's right. However, if they give you the function, then we're not supposed to estimate. Then we're supposed to get it exactly. Okay, so those are just two different types of problems that you might see. Well, let's go on to the next part of the problem.
Okay, so midpoint. Okay. I'm forgetting what exactly we do with the midpoint.
Okay, well, let's see. We want to draw some rectangles. How many rectangles are we going to draw?
4.
Good. So let's see. Show me what the width of the first rectangle will be. The first rectangle will be from where to where. Good. How can we figure out how high that rectangle should be?
By plugging in 3.5 into the function.
So you were saying a moment ago you forgot what to do with the midpoints. That's what we do with the midpoints. But before you plug it into the function, you should draw the rectangle.
Okay. Right. How could we?
So how high is the rectangle going to be? Show me its height. Show me what the height of that rectangle should be. From where to
Right
where?
here?
Okay. Now, that would be the height if we were using the right endpoint method.
Okay. So we draw from here?
Yeah. Except that line is not actually part of the rectangle, so it should be dashed. Why are we drawing that line? Just to figure out the height of the rectangle.
Okay.
All right, and now that we know the height, we should be able to draw the rectangle. Probably it would be best to draw maybe the top of the rectangle first. Okay, so the top of each rectangle should be a horizontal line. That's hard to draw on the drawing tablet, but on the test we'll try to draw the top of each rectangle as a horizontal line. You might ask your instructor if you can bring a rectangle, a ruler to the test. It might help to draw the pictures clearly if you bring a little ruler to the test. Okay, so what's the significance of the midpoint? What's the significance of the sample point? So if they tell us that we're using the midpoint method, what do we base on the midpoint?
The height.
The height. And if we're using the right endpoint, what do we base on the right endpoint?
The height.
Yeah. And if we're using the left endpoint, we base the height on the left endpoint. So that's the purpose of that. One thing notice here is, do you see why we're only using dashed lines above the midpoints? Because the line above the midpoint is not part of the rectangle. It's just a reference line that we use to figure out the height. Notice that you can't really draw that rectangle until you have that reference line, though. Because otherwise you wouldn't know what its height is going to be.
Right.
Okay.
Okay. So now we can find the area. 1 times. And then at 0.5. That's not right. Did that wrong. Okay, I have to use the function. So I need to plug these into the function. So square root 1.8 plus the square root of 1.5.
Okay, well, let's talk about that a little bit. So we've seen there's 2 different ways to find the height. One way to find the height is to approximate it from the graph, but another way to find the height is to use the formula. So at first, I think you were trying to approximate from the graph, then you caught yourself and you were using the formula. But let's be careful about how we use that formula. So what's the formula that you're using?
I'm inserting x values into the function.
Okay, that's right. You're inserting x values into that function. What's one of the x values that you inserted?
I inserted the y values.
Okay.
Great. Yeah, I'm confused. I'm not sure which x value to put in.
So we're working on rectangle A.
Right.
Let's see. So use your cursor to indicate its width. Use your cursor to indicate its width. Good. So how long is that width?
1.
So you saw that by using the values on the x-axis. Now use your cursor to indicate its height. Now that's still the width.
Right here.
Okay. So how can you figure out how high that height is?
By plugging something into the function.
Right. Well, use a dot. Remember we were using the dot method? Use a dot to show the point on the function that indicates its height. Use a dot to show the point on the function that indicates the height of that rectangle. Remember that when we did the previous problems, we were putting dots on the curve to show the points we were using to find the height.
Huh.
Well, what does that dashed line indicate?
The height.
Oh, well, there you go. So if you put a dot at the top of it, that's the point on the curve that indicates the height. Now, we have a little trouble here just because the drawing isn't perfect. If the drawing was good, then the rectangle should go through that point. If you see what I'm saying, your rectangle goes beneath that point. Maybe make a big fat dot so it looks like the rectangle is going through that point on the curve. Yes, those are supposed to be the same exact point, right? Maybe we should do that for the other rectangles where it'll be clearer. So use a big fat dot. So that point should be going directly through the function. It's hard to draw on the screen, so it's hard to get that to be perfect. Okay, well then we need to figure out the height of those dots. Let's see, and let's put in the times ones because I think the instructor is going to want to see that as part of our work. Sorry, I should have said that before,
Okay.
but you can put in the times ones times each of them. Squared, you can just kind of... Because the area is the width times the height.
All right. That's my answer.
Okay, yeah, that would be the exact answer. Let's see, I think in the answer keys, the instructor then goes and approximate that as a decimal. So let's go ahead and do that.
Okay. Yeah.
Okay. All right, well, that gave us a lot of trouble. So obviously that's a problem. We should go back and try again. Let's see, what were the issues that we had here? First of all, remember, sometimes you're going to be able to figure out the exact heights from a formula. Other times, if they don't give you the formula, you'll have to approximate them. So you have to decide which type of problem you're working on. We had some difficulty with drawing the rectangles when we're basing them around the midpoints. So what's the point of telling us that we're using midpoints? The midpoints are going to determine what about the rectangle?
The height.
That's right. That's the key. The sample point determines the height of the rectangle. The sample point determines the height of the rectangle. So we can start by drawing the height above each sample point. And maybe we should put in those dots automatically. We start by drawing the height above each sample point, and then we draw a rectangle around that. And notice that those points ended up being in the middle of each rectangle, which is appropriate because this is a midpoint approach. So you have that in your notes, and so it would be a good idea to just go back and redo this precise question again, since that gave us some trouble. This is the type of problem where the devil's in the details, so it's important to actually do the whole problem on paper so we can force our mind to think through all the little details that are necessary for getting the answer. Okay, maybe I'll go back to my screen.
Okay.
Oh, no, I had a better idea. Let's go back to your screen.
Okay.
Let's scroll back up to the graph. Something that's been giving us some trouble here is mixing up the x and the y coordinates. Sometimes we've been using x coordinates when we should have used y coordinates, or y coordinates when we should have used x coordinates. Let's actually, let's scroll up a little bit. or scroll down, sorry. Yeah, scroll down. All right, notice in your formula you had that number square root of 3.5.
Hmm.
Label the square root of 3.5 on your graph. What does that square root of 3.5, if we're going to put that number square root of 3.5 in your graph, where would it go? Hopefully that'll give us some better intuition for what we're doing here.
Right here.
Okay, now we don't usually just write a number in the middle of the air though in the graph. So where would we write that number where would we write the square root of 3.5? What does that? There you go. Good. So we can go ahead and label that. You can maybe erase the 2 and the 3 there because I don't know if they were going to be to scale with that. But anyway, that point is the square root of 3.5. That's something maybe we should start doing on these problems. I think if you do that, we'll be less likely to get confused in the middle of the problem. And then we can label that next point. Yeah. Because one thing that was going wrong on these is we were kind of confusing the x and the y coordinates. So maybe drawing more on the graph will help us not to do that. Doesn't have to be perfect. Of course, this will be easy on the real test when you're using the actual graph. So there, the dashed line should really go directly over the solid line. Oh, yeah. So, okay, good.
Something like that.
All right, so I'll go back to my screen. So to review how to do this, using the midpoint approach, we might say these are our midpoints. So to draw this rectangle, first I figure out the height of the rectangle, which goes through here. I'm just going to demonstrate this out since that gave us some trouble. So this would be our first rectangle. Maybe this is what you called A. Notice how if we draw it carefully, this part of the rectangle is under the curve, and this part of the rectangle is over the curve, and then we can extend this out and say this height is 3.5. And then here, first we figure out the height using a dashed line since that's not part of the rectangle. Then we can draw the rectangle. Notice how if we're drawing this correctly, do you see how this dashed line is at the same exact level as this solid line? Mm-hmm. This dashed line is at the same exact level as this solid line. Then for this rectangle, first we find the height. So here's our sample point. Then we draw the top of the rectangle. Again, it might help, it definitely certainly might help to actually bring a little ruler to the test.
I'm going to.
And then this point is the square root of 1.5. And if we draw it carefully, this dashed line is at the same exact level as this solid line. So notice that if we draw it carefully, half the rectangle is below the curve and half the rectangle is above the curve. And then we have this height here. Here we don't need a dashed line. Okay, so this is a little tricky to draw on the drawing programs, but when you take the test, maybe that would be a good idea to do these types of pictures, to actually label the y values here. I think it will help us to avoid mistakes if we're actually labeling the heights, these y values here, because otherwise we tend to get confused maybe in the middle of the problem and mix up the x and the y coordinates. Okay, so let's see. I think, so we had some trouble with both of those problems from the website for section 5.1. But we also don't have too much time left, so I think maybe we're getting the basic idea across. So I'm just going to move on now to section 5.2. But I would certainly encourage you to re-practice those section 5.1 problems. That's as hard as the problems get in section 5.1. We're not at the point where we're getting those right yet, but I think if you practice them, you can get them right. So let's move on to section 5.2. Now, section 5.2 is going to continue what we were doing in section 5.1. Remember, what we're doing is we're talking about the long way to calculate definite integrals. We've already learned the short way. What's the short way to calculate definite integrals? The short way to calculate definite integrals is using antiderivatives, right? But now we're going back and we're doing the long way. The long way, we're going over the long way to find a definite integral. What's the graphical interpretation of a definite integral? What's the graphical interpretation of a definite integral?
It's the area between the between the x-axis and the curve of the function.
Yeah, so basically they're areas. It's a little complicated because we treat the areas below the x-axis as negative, but basically definite integrals are areas. So what we're doing now is we're going over the long way to find areas. What's the short way? The short way to find areas we now know is to use antiderivatives. Now we're going over the long way. Well, this is the long way right here. The long way is to split the domain up into a bunch of subintervals and draw little rectangles that approximate the area. And then if you take the limit as the number of rectangles goes to infinity, that would tell you the exact area. So this is the long way to find areas, the long way to find definite integrals. So now we're just going to continue with that same process. Section 5.2 follows very smoothly from section 5.1. We're just going to introduce maybe a little new terminology. So here we said that the area was 1 times square root of 0.5 plus 1 times square root 1.5 plus 1 times square root 2.5 plus 1 times square root 3.5. Now, this type of calculation is so important that it was given the honor of being given a name. So this calculation here is what's called a Riemann sum.
Okay.
Okay, so what we've been calling, so I guess I should say this is the approximate area, not the true area. The approximate area under the curve is given by this, and that's what's called a Riemann sum. It's not the exact area, but it would get better and better as we increase the number of rectangles. So the calculations we've just been doing are called Riemann sums. So in this case, this was the Riemann sum with n equal 4 using midpoints. So what does n stand for? N stands for the number of rectangles.
Okay.
N stands for the number of rectangles. So what we did in the last problem is we found the Riemann sum with n equals 4 using midpoints. Okay. And that could also be written so we might just write that then like this. So we could approximate that as r. the Riemann sum here is equal to this. So this was the Riemann sum with n equals 4 using midpoints. Now, if you remember, we also did an earlier problem there. We did also part A. What would be the name of the sum we got in part A? I can't highlight it, but what was the name of the sum we got in part A? How would you describe it in terms of a Riemann sum?
That was the Riemann sum with n equals 4 using right endpoints.
Yeah, so notice that in both these cases, n was 4. In both cases, n was 4. But in the first Riemann sum, we used the right endpoints, and in the second one, we used the midpoints. So suppose they had written a different question. Suppose they had said, tell me when you have this question written down. Okay?
Yep.
Okay. What's the answer to that question? Well, would you agree this is the answer?
It is.
So the point I'm trying to make is the questions in section 5.2 are pretty much the same as the questions in 5.1. They just worded differently. They're just changing the wording. They're just changing the wording, but the way to answer the questions is exactly the same. So before they were saying approximate the area by using 4 rectangles and midpoints. And now they're saying approximate the integral. But remember, what's the graphical interpretation of an integral? Integrals are areas. So if they say to approximate the integral, that's the same as saying approximate the area. And a Riemann sum with n equals 4 using midpoints is just exactly what we did here. So they're just rewording the questions. They're not really changing the questions, and we'd answer it the same way. So what was the answer? The answer to this question would still be 5.38. I think 5.38 was the answer we got before for that. Mm-hmm. Okay, so suppose instead they had said this. What would be the answer to this problem?
Approximate the integral using a Riemann sum with n equals 4 using right endpoints. I think that's what we just using. Let me see. Let me check my screen. It would be 6.14626.
Okay, excellent. So what you're saying is we already did that problem.
Mm-hmm.
So if they had asked you that question, how would you solve it? You would solve it exactly the same way. We can look at that on your screen. You would solve it exactly the same way as we solved it in the previous section. You would still draw the so you still have to draw the rectangles. You still have to do 1 times 2 plus 1 times root 3 plus 1 times root 2 plus 1 times 1, and then use your calculator to approximate it. You do it the same exact way. as we did together. They've just changed the way they're wording the question. Okay, very good. All right, so I'll go back to my screen. Okay. Let's see.
So I'm guessing the textbook was just using section 5.1 as like a not a warm up, but just like an introduction to 5.2 without throwing names at you. Would that be?
I suppose, yeah, that's right.
Yeah.
So section 5.1 shows how to use this technique using more ordinary words like area. And then section 5.2 starts kind of putting in more of the math jargon, showing that what's another name for area? Definite integral. And what's another name for adding up the areas of all the little rectangles? It's called finding a Riemann sum. So yeah, in a way, it's just adding some more terminology. Of course, there's some extra stuff in this section too that we'll get to as we go along, but that's the basic idea. All right. Okay, let's try this on your screen.
So first I need to graph e to the x so I can see the function, right?
That's a good idea, yes.
So okay. I'm gonna figure out a better way to do this for tomorrow. Okay, let's see.
Good. Let's make our life easier and spread out the hash marks. All we're really going to need is the positive axis, but space your positive hash marks with a generous distance between themselves. Of course, you can always just zoom in, yeah, but.
Okay. Approximate the interval using Riemann sum with 3 rectangles between 0 and 3. Left endpoints. Okay, approximate the interval using Riemann sum with 3 rectangles using left endpoints. 1, 2, 3. Okay. So you need to plug in the function. Set area equals 1 times e to the 0 plus 1 times.
Let's see, before we write down the equation, let's label our graph. So label on your graph, label the height of rectangle A. Let's label that height on the graph first before we go down to the equation. So how would you label the height of rectangle A?
E to the 0.
Okay, good. Now let's also label the height of B. Good. So I didn't think you'd made any mistakes so far. I hadn't seen any mistakes, but we know we've been making some mistakes in the past. So before we go to the math, we should finish the geometry in the graph. I think that would be a better habit here. First, label the graph, then you can write down the equation down below.
Okay. One. Okay, so e to 0 plus
Okay. Are you done?
Mm-hmm.
Yeah. Now, so what was the answer?
I found the area, and it's approximately 11.107.
Good. What was the question asking us for?
approximate the integral using Riemann sum.
So instead of calling it the area now, we should call it capital R. Remember that we've changed our jargon here. So instead of calling those A, we should call those capital R. Now we're treating those as Riemann sums. All right, so do those give us the exact value of the integral? Well, no. Remember, we're approximating the integral. They give us the approximate value of the integral. Are they under or overestimating the integral?
We're underestimating.
You can see that from your picture. You can see from the picture that they don't include all of the area. How could we get a better approximation to the integral?
We can get a better approximation by taking the right endpoints.
Possibly, but that's not really what I was going for here. The key thing is we can get a better approximation by using more rectangles.
Okay.
I want to keep emphasizing that because that's the whole reason that we're studying this. So how could we get a better approximation to the integral?
Need more rectangles.
More rectangles, that's right. Another way of putting that is we could get a better approximation by using a bigger n. If you see what I'm saying?
Mm-hmm.
Because what does n stand for?
The number of rectangles.
That's right. So we could get a better approximation by using a larger n. For example, if we used n equals 1,000, the approximation would be pretty darn good, right? So we can get a better approximation by using a larger n. Okay, so how could we figure out the exact integral? How could we figure out the exact integral? You could figure out the exact integral by taking the limit as n goes to infinity. We could figure out the exact integral by finding the limit of the Riemann sums as n goes to infinity. Does that make any sense?
Mm-hmm.
Yeah. So how could we get a better approximation? We could get a better approximation by finding the Riemann sum for a larger n. We could get a better approximation for the integral by finding the Riemann sum for a larger n. And how could we get an exact value of the integral? We could find an exact value of the integral by taking the limit of the Riemann sums as n goes to infinity. So notice, do the Riemann sums equal the definite integral? Do the Riemann sums equal the definite integral? No. The Riemann sums approximate the definite integral. The Riemann sums approximate the definite integral because they approximate the area. And the bigger n is, the better the approximation is. And the limit of the Riemann sums as n goes to infinity, that does equal the definite integrals. I guess those are kind of subtle ideas, but that's what they're trying to teach us here in this section. Okay, so it looks like that came out correctly, so I'll go back to my screen. All right, now let's try this problem. And you got that graph by graphing it on your calculator?
Mm-hmm.
Okay, yeah, that was a good idea.
Okay, so now we're using right endpoints. I'm just going to ignore this guy for now. So we go up.
Good. Maybe the first thing you should do is draw the sample point and then draw the rectangle. That's good that you labeled the axes. And that's good that you labeled all the coordinates before you started drawing the sum.
So now we do rectangles 1 times d cubed. D cubed plus d squared plus g. Okay.
Okay. Good. Yeah, that came out correctly. Okay, good. So that's some good progress on that. So what's the meaning of that Riemann sum? Remember, the Riemann sum approximates the definite integral. It approximates the definite integral, or it approximates the area. How could we get a Riemann sum that gives us a better approximation?
By using more rectangles.
Yeah.
Like
or by increasing n. That's right, which increases the number of rectangles. How could we figure out the exact value of the definite integral? How can we find the exact value of the definite integral? We can find the exact value of the definite integral if we take the limit of the Riemann sums as n goes to infinity. We can find the exact value of the definite integral if we take the limit of the Riemann sums as n goes to infinity. Just like if you remember the long way to find derivatives, you can approximate the slope of the tangent line with the slope of the secant line. You can approximate the slope of the tangent with the slope of the secant, and the closer the points are to each other on the graph, the closer the secant line is to the tangent line, and the limit of the slopes of the secant line as the points get closer and closer is the slope of the tangent. It's a difficult idea, but it's the same type of a thought process as we did for derivatives. That's what they're trying to get us to see here in these sections. Okay, I'll go back to my screen. But that was a good systematic process for that last problem. And let's try this.
Okay. All right.
Okay. Let's see. Okay, good. That looks right. So going back, all right, so that's some improvement on that midpoint approach. The midpoint approach was giving us trouble before, but now we have a more systematic approach for that, so that's good. Take a look at the right endpoint picture again. Did that right endpoint picture over or underestimate the integral?
It overestimates.
Because you can see the rectangles are are bigger than the area. And how about the left endpoint approach if you scroll up?
It underestimates, and we can see that because the rectangles are below the curve.
Right. And how about the midpoint approach? Was a little hard to tell. The midpoint approach, each rectangle has some area that shouldn't be included, and it's also missing some area that should be included. So it's not immediately obvious whether it's under or overestimating. We can guess it's probably going to be closer to the true answer. Okay, that's just to improve our intuition here a little bit. So how could we get a better approximation than this Riemann sum?
We could use more rectangles.
That's right. And how could we get the exact value? We could get the exact value by taking the limit of the Riemann sums as the number of rectangles goes to infinity. And what's the symbol for the number of rectangles?
The number of rectangles is infinity.
What's the symbol for the number of rectangles?
N.
N. So we could take the limit as n goes to infinity if we wanted to get the exact value. Okay, good. All right, so these are ways to approximate the integral. Now remember, you and I have already learned how to find the exact value of the integral. Why don't we go ahead and do that? Let's figure out the exact value of this integral.
Okay.
Great. Why did you still write an e to the x inside the brackets?
Because the antiderivative of e to the x is just e to the x.
Yeah, it doesn't usually work that way, but it works out that way for e to the x. Good. Okay, and let's get a decimal answer to that. How does that compare to our approximations?
It's fairly close to the midpoint, not a bit far from.
Notice that the right endpoint, as we expected, overestimated. And the left endpoint was only 11, so that underestimated. The midpoint in this case was pretty accurate. The midpoint isn't always the most accurate, but it's probably usually the most accurate approach. But in any case, you can see, even with only 3 rectangles, the midpoint approach was a pretty good approximation. You can see if we used 1,000 rectangles, it would be a great approximation. Let's also do that on your calculator and get the exact value on your calculator.
Okay. I get 19.085537.
So you got the same answer. Same answer as before. Okay, very good. How does your calculator figure that out? How did your calculator figure out that integral? Well, I don't expect you to know. I'll just tell you, your calculator can't do calculus. Your calculator, there are calculators that can do calculus, but your calculator can't. Your calculator doesn't actually, so your calculator doesn't know that the antiderivative of e to the x is e to the x. Your calculator can't do calculus. So how the heck did your calculator figure this out? Well, the answer is the calculator did a Riemann sum. Or something like that. I think it used a Riemann sum. It did a Riemann sum with probably maybe n equal to, say, 1,000 or 2,000 or something, right? Of course, if we were going to do a Riemann sum with 1,000 rectangles, it would take us all week and it would be very unpleasant. But that's the great thing about computers and calculators. They don't mind all that drudge work. So the way your calculator is actually calculating these integrals, it's only approximating them. It's doing a Riemann sum with just a very large n, maybe 1,000 or so, I don't know, which it can do very quickly because it's a calculator. Okay, so when you have a large enough n, the Riemann sum becomes almost exactly equal to the real value. So I'll go back to my screen now.
Okay.
So do you see what these dots here mean? I'm trying to add 100 numbers, but I'm too
Right.
lazy to write all the numbers in the middle. All right, so this means we're adding up 100 numbers. Now, the dots just stand for the missing numbers. Now, mathematicians actually have another notation for this. Mathematicians' notation for this is this symbol. You've probably seen this symbol now in class.
Yeah, just today.
Okay, so this is called a sigma. This is a sigma. It kind of looks kind of like an E, a weird looking E.
That just represents sum, right?
Yeah, so sigma is the Greek letter for S. And so the mathematicians chose it because this stands for sum. So this is a shorthand for this sum. This is a shorthand that's even shorter than using the dot notation. So the point here is, notice what it says here is that you're going to first plug in 1 for I. And then what do we plug in for I next?
2.
And then what do we plug in for I next?
3.
And then what do we plug in for I next?
4.
And you'll just keep on doing that forever and ever and ever until, what's the last value you're going to plug in for I?
100 in this case.
That's right. So I'm just trying to explain what these symbols mean. So this is a shorthand for this sum. Again, this is the same as this. Just a shorthand that they use to write sums in a more compact notation. Okay. So how could I write this out? Obviously, this is a sum. What's the first term in the sum?
X subscript 1.
Not quite. You have to pay attention to how I've written this differently. The first term here is f of x1. If you see, do you see how these are different from each other?
Mm-hmm.
And what's going to be the next term in the sum?
The f of x2.
That's right, because now you plugged in 2 for I. And what's going to be the next term in the sum?
That would be f of x3.
And the next term?
F of x4.
So in that case, you plugged in 4 for I. What's going to be the last term in the sum?
The f of x50.
Okay, so this is just another variation on that notation. Remember, this is called the sigma symbol. The sigma symbol. Sigma symbol. All right, good. Let's see. So what's the first term in this sum?
Let's see. That would be f of x1 times sine of a. Plus f of x2 times sine of a. plus f of x3 times sine of a dot 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 f of xn times sine of a.
So are these x values changing in each term?
Yep.
Yeah, because x1 could be different from x2, which could be different from x3, which could be different from x4. Are the a values changing?
They're not.
How can you tell they're not changing? You can tell because there was no I here. If there was an I here, then the a values would change too, if you see what I'm saying.
Mm-hmm.
Yeah, but since there's no I, the a values are all the same in each case. In fact, if you wanted to, you can now factor out the sine of a. You could factor out the sine of a from this. You could factor out the sine of a from that sum. Okay, so that's a little practice. You could even factor out the sine of a from this expression. That's a little practice with this sigma notation. So let's see. How would we then figure out okay, so let's say that we had this problem.
Right.
Now, we already know how to do this the short way, right? I think we just talked about this a moment ago. The short way is to use antiderivatives. Now, what's the long way? Well, first of all, notice now they're not telling you to approximate it. They're not telling us to approximate it anymore. Now they want us to find the exact answer. How could we find the exact answer? Well, we could start by saying we're going to make a whole bunch of little rectangles. All right, I'm not going to draw every single rectangle, but I'll finish it off up here. Dot, dot, dot. So we're going to split up this whole thing into tons and tons of rectangles. What's the symbol for the number of rectangles we've used?
N.
So let's say we have n rectangles. All right, so I'm getting up to maybe 30 or 40 I would have done here. So then how would we find the area of each of those? Well, first of all, what's the width of each of these rectangles? What's the width of each of these rectangles? Well, we could use the symbol delta x for that. Do you see why that's a good symbol?
Yep.
Because delta x is the distance on the x-axis. So this would be delta x in this case. And then, for example, those rectangles are terrible. All right. How do we find the height of this rectangle?
By plugging in the width, by plugging in the x value or the endpoint that we're using.
Plug that into
function.
what?
The function.
Yeah, f of x. So remember, we have to pick a sample point from each interval. we're going to have to pick a sample point from each interval. So what do we call the sample point for the first rectangle? We could call it x1. And what do we call the sample point for the second rectangle? We could call it x2. And what do we call the sample point for the third rectangle? We could call it x3. And what do we call the sample point for the 20th rectangle? We could call it x20. So let's say this is the 20th rectangle. Then the sample point here would be x20. So it might be a left endpoint or a right endpoint or a midpoint. So then if the sample point was x20, how would we find the height?
If it was x20, we plug in 20 into the function.
Well, no, because we're not saying that this point here is 20. Obviously, it's not 20, right? It's less than 2.
Right.
What would we plug into the function? We wouldn't plug in 20. We'd plug in x20. This is what I mean by x20. It's just the 20th sample point. The 20th sample point. So how would we find the height of this rectangle?
By plugging in the 20th sample point into the function.
So what should I write here?
F of x20.
Right. And then here's the 21st rectangle. How would we find this height?
F of x21.
That's right. And here's the 22nd rectangle. So what would its height be?
It's F of x22.
So what's going to be the area of the first rectangle? Well, its width is this, and its height is this. Would you agree that's the area of the first rectangle?
F of x1 is its height times delta x. Yep.
And then what's going to be the height of the next? So then what's the height of the next rectangle?
F of x2 times delta x.
And then the next term?
F of x3 times delta x.
And then the last term?
F of x.
So what's the symbol for the number of rectangles?
N.
So I didn't tell you how many rectangles there are. Let's just say it's a big number, n.
Okay. F of xn times delta x.
So this would be the Riemann sum for n, right? This would be the Riemann sum. Now we want the exact answer, though. Well, the exact answer would be
N is infinity.
right, except we have to be a little careful. Infinity is not an ordinary number. You can't just plug in n equals infinity. That doesn't really mean anything. How could you can't really have an infinite number of rectangles, right? You can't actually have an infinite number of rectangles. The trick is to take the limit as n approaches infinity. So the integral, this integral is exactly equal to this limit as n approaches infinity. This is the long way. Obviously, this is much more painful than using the fundamental theorem of calculus and antiderivatives, but this is the long way to find definite integrals. This is kind of the definition of definite integrals. So the long way is to take the limit as n goes to infinity of this sum. Now, it's kind of a pain to write this whole thing out. Wouldn't it be nice if mathematicians had invented some kind of shorthand for summarizing long sums? Well, we think we talked about that shorthand a few minutes ago. We can summarize this sum using the sigma notation. So remember that in sigma, when we're using sigma notation, we invent a new variable I. And what's the smallest value that I will take in that sum?
0.
Actually, no. I stands for these subscripts.
Okay.
So the smallest value that I will take is 1.
Okay.
Notice I is not standing for the x's. I doesn't stand for the x's, I stands for the subscripts here. And then what's the biggest value that I could take?
N.
Because that was our biggest subscript.
Mm-hmm.
And now here we have to kind of write a general formula for the terms that we're adding up. So what could I write here?
Let's see. General formula.
That's going to summarize this sum in the sigma notation. 1 second though, my pen's not working. So you'll have a few seconds to think about it.
Let's see. The sum.
Remember, here was an example
Yeah,
of how we went
understand.
from sigma to here, or here's an example. Let me get my pencil to work. Oh, the pencil's back. Okay, time's up. No. So how could we, what goes next to the sigma here to summarize this sum?
F of x. I'm not sure how to express it, but from 1 to n.
What we're trying to write down here is kind of like a typical element in the sum. Well, what's the name? I can't write x1 because that's only one of the elements in the sum. I can't write x2 because that's only one of the elements in the sum. I need some general expression for the subscript. Well, that's where the I comes in handy.
Okay.
This is f. So notice I is just a new made-up variable, that we make up to help us rewrite this sum. And then what goes here?
Delta x.
So this is the mathematician's way of summarizing this sum. This is the mathematician's way of summarizing the sum. And now we have the expression. This is the answer to the question. So this is this is how we would find the integral the long way. The long way to find this integral is to find the limit of the Riemann sums as n goes to infinity. Find the limit of the Riemann sums as n goes to infinity. Okay. Another way they could put this is they could say, this is actually how they put it usually in your class. They say, express this integral as the limit of Riemann sums.
So would that formula be the same for any? So would that formula be equivalent to any definite integral because it doesn't seem specific to the 0 to 3?
That's an excellent point. That's right. That's a good point. Here we didn't actually use the function in any way, and we didn't actually use the limits of integration specifically. So far, I'm trying to explain why this makes sense because I think it's important to understand it. That way you can adapt if the questions are a little bit different. But you can also kind of just memorize that this is the answer to this type of question because you're right, the answer is not going to change very much. It's always going to be written pretty much like this. Now, we can go into this a little bit more detail here, though, to see how it can be different. First of all, what are the xi's? What are the xi's? Those are the sample points, right? Mm-hmm. Those are the sample points. By the way, notice it really doesn't matter whether you think of the xi's as left points, right points, or midpoints. Because do you agree, if the rectangle is small enough, the answer from the left endpoint approach is going to be almost the same as the answer from the right endpoint approach, and that's going to be almost the same as the answer from the midpoint approach. When you take the limit as n goes to infinity, it really doesn't matter whether you think of xi as being a left point, a right point, or a midpoint. It doesn't matter. The limit will be the same no matter which point you use because you can see from these little rectangles, the height of the right point is almost the same as the height of the left point, and that's almost the same as the height of the midpoint. So we don't have to worry anymore. When you're taking the limit as n becomes huge, you don't need to worry about whether the x's are right points, left points, or midpoints. But anyway, what do the xi's stand for? They're the sample points. Sometimes in your class they're written like this. Sometimes in your class they write this with a star. They're not consistent. Sometimes they use a star, sometimes they don't. So what does this symbol stand for?
The sample point?
Yeah, the sample points.
And the sample point is Just an x value, right?
It's an x value inside the interval.
Okay.
So x1 is a sample point inside the first rectangle.
Okay.
x2 is a sample point inside the second rectangle. x3 is a sample point inside the third rectangle. Which sample point is it? Well, who cares? It doesn't really matter. When the rectangle is tiny, it doesn't matter what sample point you use. They're all going to give you approximately the same answer anyway. So when you take the limit, it's still going to go to the same limit. So what does this symbol stand for?
Sample point.
Inside which rectangle?
It doesn't. It's not specific to all rectangles.
Well, the better way to put it is this is the sample point inside the ith rectangle.
Okay.
This would be the sample point inside the ith rectangle. All right. What does this stand for?
The sample point inside the sixth rectangle.
Good. Now, what about this delta x? Would you agree that as n increases, delta x is going to change? The more rectangles there, when you increase the number of rectangles, that changes the width of the rectangles, right?
Mm-hmm.
As n goes up, is delta x going to get bigger or smaller?
Smaller.
So this is not good enough. We have to tell how we're finding delta x. Well, this is something you and I have worked on before. If these are the limits of integration, how would you calculate delta x?
3 minus 0 divided by n.
Perfect. Excellent. Good. That's why we were writing those out before. So the total width that we're trying to account for is from 0 to 3. And we have to split that up into n subunits. So this would have to be part of your answer.
Okay.
By the way, you were saying before that this doesn't seem specific at all to the problem. It seems like you could write down the same darn thing every time. Well, that was right, but this is specific to the problem, right? This part is specific to the problem. Also, I think on some problems they might want you to be more specific. Let's try to write a more specific expression for f. Well, what would be a more specific expression for f of x1? How could we be more specific on this problem? What would be a specific expression for f of x1?
Okay, that would be e raised to x1.
Okay. You avoided the trap. You avoided the mistake. The trap would be to say this. I think that would be an easy mistake to make. We're not raising it to the first power. We're raising it to the first sample point.
Mm-hmm.
Good. So then what would be f of x2?
E raised to x2.
Excellent. So what would be f of xi?
E raised to xi.
What does this mean? This is the height of the ith rectangle, right? This is the height of the ith rectangle. Well, how would you find the height of the ith rectangle? You would take the ith sample point and plug it into the function. So here maybe is what they might actually be going for in this problem. So what can I write down here for, instead of writing f of xi, how can I be more specific?
We can write e to xi.
That's right. In this case, maybe that's what they'd want because they actually gave us the function. Since they actually gave us the function, maybe this is what they'd want as the answer. And then we can still write delta x. So that goes back to the comment you made earlier. You were saying this seemed weird because it seemed like you could write the same exact thing for every problem. Well, not if they're going for this. So in this case, now you can see how it's going to be a little bit different for every problem. You still might want to memorize this stuff up front. Hopefully I explained why this makes sense, but maybe you should also just memorize that these are the symbols that we start with. So the idea here is, how do we find the definite integral? Well, you write down the you imagine that you've drawn n rectangles. This is how you would find the area of each separate rectangle. You need to add up all the rectangles. So this means we're adding up the areas of all n rectangles. We're adding up the areas of all n rectangles. Now, if that was all you did, you'd only get an approximation. If all you did was just add up the areas of n rectangles, that would only approximate the integral. But if you take the limit as n goes into infinity, that limit is the exact value of the integral. So now we've seen this is the long way. This is the long way to find definite integrals. Now the good thing is your instructor is going to say this. this is a big load off our backs, you're not actually going to be required now to calculate this limit. You remember that when we did derivatives, you actually had to calculate the limits, right? Remember when we did derivatives, we didn't just write down that the derivative was the limit of the slope of the secant lines. We actually had to do a bunch of algebra and actually evaluate the limits. But your instructor is going a little easy on your class. Your instructor is not actually requiring you to evaluate the limits. They're just asking you to write down the limit. So we can stop right here. So this will be a little easier than when we've had to learn the long way for derivatives. So I suppose that if we did enough algebra, we could actually prove what the answer is here, but we won't have to get into that. We're not actually going to have to do the limit. We just have to write the problem, in a sense, not the answer. Okay, so here's another type of question that I think you're going to see on the test. A question like this. This is another type of question from section 5.2. So they might give you a question like this. Express this integral as a limit of Riemann sums. Do not evaluate the limit. And then I suppose this would be the best answer right here. So we can work more on that tomorrow, but that gives you a first look at that. So that would be a good thing to review. It would be good to kind of meditate on this last stuff that we were talking about here. Obviously, we'll have to build on that tomorrow and redo maybe some of those midpoint and endpoint problems that we did before so that we're comfortable with those as well, because we're going to have to keep building on that. Make sure you understand the sigma notation that we've been talking about here. So basically tomorrow we're going to try to build on what we were just talking about.